For our project, we did option number 4, which was to read the majority of section 11, which was the direct product of groups, and report a summary plus a couple of problems. The first definition we had was the definition of the Cartesian product. The Cartesian product is the set of all ordered n tuples or of two or more sets, A1, A2 to AN. The Cartesian product is denoted either by S1 times S2 times S3 times Sn, or the product such that I is equal to 1 to n of S sub I.
The direct product of groups is the result of finding the Cartesian product where the sets are groups under a defined binary operation. And the direct sum of groups is the direct product of groups when the binary operation is commutative.
For the first problem we needed to find the elements of Z3 times Z4, and then find the order of each of these elements and answer the question, is this group cyclic? The elements we found are listed below here, as well as all of their orders. A direct product of groups is cyclic if the order of the generator is equal to, in this case, 3 times 4, or generalized m times n. Thus, we can see that when the generators are 1, 1, 1, 3, 2, 1, and 2, 3, the order is 12. Thus, it is cyclic with those generators.
All right, so number 4, we had to find the order of 2 and 3 in Z6 times Z15. The first thing we must do is to find the order of 2 in Z6. In order to do this, we start by finding the greatest common denominator. GCD of 2 and 6 is 2. We then have to divide the order of 2 in Z6 by the order of Z6, and 6 divided by 2 is 3. We now see that 2 is of order 3 in Z6. We then repeat the problem for 3 in Z15, and the GCD of 3 and 15 is 3, and 15 divided by 3 is 5. We see that 3 is of order 5 in Z15. Now we must find the lowest common multiple of the order of 2 in Z6, and then the order of 3 in Z15, and the lowest common multiple of 3 and 5 is 15. Thus, the order of 2 and 3 in Z6 times Z15 is 15. And for number 6, similarly to number 4, we must find the order of 3, 10, and 9 in Z4 times Z12 times Z15. In order to figure this out, we must find the order of 3 and 4, 10 and 2, and 9 and 5. And so the order of 3 and 4 is 4. The order of 10 and 12 is 6. And the order of 9 and 15 is 5. Then we must find the lowest common multiple of 4, 6, and 5, which is 60. Thus, the order of 3, 10, and 9 in Z4 times Z12 times Z15 is 60.
For number 8, the original question was to find the largest order among the orders of all the cyclic subgroups of Z6 times Z8 and Z12 times Z15. Instead of brute forcing this, I found the problem simply by taking the lowest common multiple of 6 and 8 and 12 and 15. However, I had no way to prove that that would be the largest order. So instead, I worked on this rough proof that shows how to find the order of the largest order among any orders generally, and what those generators will be. So we know that the order of x in Zm is the GCD of xm, and the same goes for y in Zn. Therefore, the order of x in m will always be a divisor of m, and the same goes for y in n. Therefore, the largest possible order will always be created by the LCM of m and n. However, there can be more than one set of numbers that share an LCM when you look at divisors. If we look at all the prime divisors of m and n, they can share any number of values. We will call those shared values prime 1, prime 2, prime 3, all the way up to prime n. If you recall the fact that when we're using prime factors to find the lowest common multiple of any two numbers, you only use those shared values once when multiplying the prime factors. Therefore, you can divide either x or y by any p1, p2, p3 to pn, and you will have the same LCM of m and n, meaning it will still be the largest. Thus, any coordinates xy such that x and y are equal to m and n divided by any of the values from p1 to pn, as long as none of the p1 to pn values are repeated, this will produce the largest possible order. Number 46 was a little bit easier. To prove that the direct product of abelian groups is going to be abelian. So for this, we let gi, which would be any groups, we are specifying 2, where I is less than n, or equal to n, and I is an element of the positive integers. In order to calculate the direct product of n groups, we use the corresponding group operations in each of the n components. In this case, we know that those group operations will always be abelian. We also say that we are defining a1 to an and b1 to bn as the two elements of the product of gi, such that ai and bi are elements of gi. The commutative law in the product is then thrown back onto the commutative property of each of the groups. We can see here that when multiplying through, a1, b1, a2, b2 is equal to b1, a1, b2, a2, all the way to an, because we know that both of the binary operations are commutative. Therefore, we can say that is the same thing as multiplying b1, b2 to bn and a1, a2 to an, therefore saying that the direct product of two abelian groups is abelian. Hi, I just wanted to come back. Throughout the editing process of my video, I did find a mistake I made in this proof, which left me a little stumped. So I just wanted to bring that to light. It is right here in this line. The order of x in Zm is not the GCD of Xm. The order of x in Zm would be the GCD divided by m, meaning it is m over the GCD of Xm. That left me a little stumped. I believe there is still a connection between the shared prime divisors and the tuples that make the largest order. However, I've struggled to find it. Yet I also realized I did not answer the question in its entirety. One thing I did learn is both can be made by 1, 1, meaning that my point staying that if x and y are equal to m and n being the modulus of z, you do get the largest order. However, I'm not sure what other work needs to be done. So the largest orders in this case are 24 and 60, or the LCM of 6 and 8, and the LCM of 12 and 15. Yet where this proof will take me, I am not sure, and we'll work on it at a later date.